Ionic, covalent, metallic compound. Let's look onto the periodic table again, onto this metallic compound, ionic compound, covalent network, and covalent molecule. Let's start off with metallic compound and ionic compound and see the difference. Metal have certain feature. First, usually metal, you notice they have quite a high melting point. Could be about 1000 degrees or above for the metal to be melted. They have high density. That means they're quite heavy. And you can see most of the metal, they have a shiny surface. And two important features too. They all conduct heat and electricity well. And they when you heat it up, they're quite malleable and ductile. I'm going to talk about this feature a bit more detail. First, metal. You notice all metal, they conduct electricity well. In metal structure, it consists of the positive metal ion and surrounded by a sea of mobile electrons on its outer shell, so it moves freely around atom. So these outer electrons we call it delocalized, and these electrons are not associated to any particular metal ion. Now, what do I mean by delocalized? What I mean by sea of mobile electron? If you look onto the picture a bit more detail, on metal ion, you will see on this picture there is a lot of white dot that is representing the electron movement. And this electron, as you remember on periodic table of the group 1 and group 2 of the metal, they all tend to lose out the electron. And this losing out electron will very easily to moving around the atom, and it will moving from one atom jump to another atom. So when they jumping around, so we call this become delocalized. So this electron doesn't belong to one atom anymore, but rather they can move around to another, to its neighbor. So we describe it when you have a group of metal ion together. This electron will be in one big group, like a sea of mobile electron. Like a big amount of fish swimming across the ocean. So you can see a lot of electron jumping across. And this electron, that's what we describe it as a mobile electron. And this mobile electron explaining the property why metal conduct electricity well, because of this electron can easily move across. And it also explains why it conduct heat well, because the electron can easily, when you hit from one spot, those vibrate electrons can easily jump across. That's it explains about these electroconductivities. Let's look on to another feature. Most metals are quite malleable and ductile. So what do I mean by that? So you can see that although metal, they have this lattice structure, this metal ion, they have little restriction. So one layer of iron can slide over another. You can see that at the bottom of the picture, the metal iron, they are in quite a well aligned. So you can imagine like a box of orange. They are in quite a nice alignment. So if you are in a nice plane of alignment, imagine if you apply force against one layer to another layer, the layer can quite easily to slip past. So you can see in the olden day, the blacksmith, they can heat up the metal and hammer it into a sheet or draw it into a wire. So metal are quite malleable and ductile. Now I'm going to look onto the ionic compound. What is ionic compound? I hope students still remember ionic compound is come from the metal react with non-metal, the positive ion and the negative ion. As example, NaCl, it consists of the positive charge. They consist of the positive charge and the negative charge. And these positive negatives help together by this electric attraction, so to form into this lattice structure. So this electrostatic attraction is this ionic bonding, and they also have quite a high melting point. Example of it, NaCl. What is the common name of NaCl? Salt, the salt that we eat. And they have quite high melting point. Now let's look onto another feature of this ionic compound. Something that you might not realize. Ionic compound, when a piece of salt, they do not conduct electricity. So when ionic compound in a solid state, they do not conduct electricity because these ions are in a fixed position and they cannot move. But something unexpected is when they are in an aqueous solution. That means when they are, for example, when they dissolve in water, they conduct electricity. So, and the ion can move freely around. So, in one experiment, if you have a battery with two metal rods, and if you put a spoon of salt into the water, that you contain the positive, negative ion now, you will find that they conduct electricity very well. Ionic compound, which will be different from the previous example, metallic compound, they are quite brittle. If a layer of ions is to force past another layer, this orderly arrangement will be disrupted and this crystal will fracture. So when you apply force onto the ionic compound, they don't have this slippery plane, but rather they will simply crack. So you can see compare the metallic compound with ionic compound. First, they both have high melting point. Metallic compound, they have quite a shiny surface. Ionic compound, on the other hand, usually a dull surface. Metallic compound, they all conduct electricity and conduct heat, and which is different from ionic compound. Ionic compound, when they are a solid, they do not conduct electricity. But when they are in solution, they conduct electricity well. Metallic compound is quite malleable and quite ductile, which different from ionic compound. They are quite brittle, like a piece of salt. You hammer it, they simply crack. Okay, after we look onto metallic compound and ionic compound, I'm going to move on to another two groups, the covalent network and covalent molecule. What is a covalent network? Covalent network is atom joined by a strong attraction force that is a strong covalent bond. And this covalent bond, as you know, all non-metal react with non-metal form covalent bond. They create a rigid three-dimensional structure. They form a rigid three-dimensional network structure. Pay attention to this sentence. Rigid three-dimensional network structure. So this gives it a property of a very high boiling point, extreme hardness, non-conducting electricity, and insoluble in water. And I'm going to give example, diamond, rock. Now I want to explain how these strong covalent bond affect in this rigid three-dimensional network structure mean. If you look onto the top example of the diamond, you see that when I blow up the size, actually they are made of a carbon atom. But when you look closely with this carbon atom, you will see this carbon atom on each side, they bonding to the other atom, and this carbon also bonding to another atom, and as it bonding to another atom. So this forming what I mean by this rigid three-dimensional network structure. And how long would this bond be continue? Almost infinitely. Could be a million or 100 million of this atom molecule all bind together into a not movable, strong covalent bond. Now let's look onto the bottom structure, rock, commonly like the granite stone. That is another example. They are also by covalent bond, and you can see they also have a three-dimensional rigid structure. Each one bond with the other neighbor, and the other will bond with the other neighbor, forming into an infinite 3D network structure. So how big can it be? Could be another million, trillion of atoms all bond together to each other into a total rigid structure. This explains why you have such a high boiling melting point. So if you imagine to melting a rock, it takes 3,000 to 4,000 degrees, even higher than melting metal. And when you talk about hardness, diamond is the hardest substance on earth. So they give it an extreme hardness. And as we know, most non-metal they have no outside electron can moving around. They will always attract electron, so they don't give electron, so they do not conduct electricity. And rock, not soluble in water, and everyone knows. So this is the feature of covalent network compound. Now, I'm going to introduce another type. This is called the covalent molecule substance. This covalent molecule. And they also are held together by a covalent bond. As example, oxygen, carbon dioxide, water. As I show onto here is the water, carbon dioxide, hydrogen chloride, ammonia, and you can see they all are a molecule. But if you examine the property, something will give you very unexpected result from the last one. They will be very low boiling melting point. Last example, it takes 4,000 degrees to melting rock. And this property quite opposite. They are low boiling melting point. Usually at room temperature, you will find them usually will be as a liquid or as a gas state. So usually you'll find it as a liquid or as gas. Even if you lower the temperature enough, they form into solid. This solid will be quite soft and waxy. And you will wondering, how come they both are covalent bond? How come you have such a different property? One early example, extreme hot, extreme high boiling point. And this example is extreme low boiling point and extreme soft and usually liquid and gas. Now let's look on to the bottom of the picture. I hope this picture you will know. Look, what is the attraction force between the molecule? The molecule in between, within it, that is covalent bond. As here, what is the attraction force in between? Within it, that is covalent bond. As water, covalent bond, covalent bond, covalent bond, covalent bond. But when you look onto more closely, now you see what is the attraction force between one molecule with another molecule. That is the intermolecular force. What is intermolecular force? Hydrogen bond, which is around 100 to 200 boiling point. What else? Dipole, which is 0 to minus 100, or disperse force, which is around minus 200 to minus 300 degree. So they all are very weak attraction force. They are a weak attraction force for this intermolecular force. And this explains what, yes, you can say, yeah, within the molecule, they are covalent. As you see, here is the covalent, and here is the covalent. You want to break this covalent, you take 1,000 degrees. But to break this intermolecular force, maximum 100-200 degrees is good enough. And this explains the property of this covalent molecule. Why you have such a low boiling melting point, and they always will be liquid or gas at room temperature. Now we learn about this covalent network and covalent molecule. You will notice covalent network have such a very high boiling melting point because of this 3D network, each one bond together, different from the covalent molecule, which they have the covalent network, they have the covalent bond and also the intermolecular force, which are weak, so give it a liquid and gas in room temperature. The top one covalent network are extreme hard and strong, which opposite to the bottom one. Even you can make it into solid, they still soft. Summary: metallic compound, ionic compound, covalent network compound, and covalent molecular substance. And now this is the ionic covalent metallic compound. Thank you.